Welcome to Lecture 3.3, Solving Differential Equations with Fourier Series. Let's begin with some motivation. Recall from the previous section the method of undetermined coefficients to solve a second-order linear inhomogeneous ODE. So one like this, y double prime plus a of x y prime plus b of x y equals f of x. Now f is the forcing term. Now previously we usually did these where t was the variable, but now we're going to use x. It doesn't really matter. To do this, we first solve the related homogeneous equation. We set the right-hand side equal to 0, and we solve that. Then we had to guess the form of a particular solution, yp of t, and we added those together to get the general solution. Let's recall how we would guess a particular solution. Our general rule of thumb is that it should have the same form as the forcing term f of x. For example, if the forcing term was an exponential function, e to the kx, then we guessed a particular solution of the form a e to the kx. And the reason being, because if we plug this back into the left-hand side of the ODE, we get some number of e times k to the x. And if we set a to be just right, the right-hand side is an e to the kx as well. We can get those to cancel. Similarly, if the forcing term was a degree k polynomial in x, then we assume that there is a particular solution that's also a degree k polynomial for the same reason. If the right-hand side is this degree k polynomial, and we take this degree k polynomial and we take derivatives and plug it into the left-hand side, then we still get a degree k polynomial. So we can equate like coefficients. Set the coefficient of x to the k equal to ck, and so on. Finally, if the forcing term was a sine or cosine wave, like sine of kx or cosine of kx, then we guess that there's a particular solution of the following form, a cosine of kx plus b sine of kx. Because if we plug this into the left-hand side, take derivatives and so forth, what we end up getting is some number of cosines and some number of sines, and the right-hand side, whether we have sine or cosine or some linear combination, is the same thing. Of course, there were other examples than just these. Some more complicated ones we did not cover in this class, things like what if you have the product of two things like this? Or there were, of course, some annoying cases as well, like when our guest actually solved the homogeneous equation and we had to multiply by a t or an x. So these are just the basics, but if you understand the reason for these guesses, you should understand what we're going to do in this lecture. Here's the big question of the lecture. What if the forcing term is a piecewise function like a square wave? So for example, what if our forcing term, and this is completely reasonable if we have something like an electrical signal, is discontinuous, but it's like this. Now our calculus methods break down. You can't just take the derivative of this and plug it back into the left-hand side and try to solve. So what do? Well, one answer is to use Laplace transforms. You may remember, if you've studied this, that anytime you have a piecewise function like this, you can represent this nicely with the Laplace transform, and then there are methods for turning that Laplace transform into an algebraic equation and solving ODEs that way. It's a big, complicated process, and I think I have an entire lecture that is basically this example of a simple ODE with a square wave forcing term. And the square wave is about as simple as you can get. It's a constant function that repeats like this. So this is not ideal. I'm going to show you a new method today. And our new method is basically our old method of undetermined coefficients, where we're just going to guess that the particular solution has a certain form. So what do you think we should do if our forcing term is a square wave? What do you think our guess should be? You should pause the lecture to see if you can figure it out before I move on. Okay, ready? I'll tell you. Let's assume that it is a Fourier series, where L is the period of the square wave. So f of x can be written as a Fourier series, so it makes sense that there should be a particular solution that has the same period, and that will have a Fourier series as well. So we're going to guess that yp is of this form. We're going to take derivatives of this, plug it into the left-hand side, and equate coefficients and figure out what the ANs and the BNs have to be. Once again, this is generally much easier than using Laplace transforms. We'll do two examples in this lecture. The first one is more complicated. I'm doing it first because the second one, I'll show you how to use some shortcuts that sometimes work. So everything here should be familiar from previous lectures. We've seen the left-hand side of this ODE when we studied undetermined coefficients. That was our running example. And we computed the Fourier series of this function in the previous lecture. So if you haven't seen those lectures, please watch them now. Okay, let me sketch what this looks like first of all. So this square wave looks something like this. This is that's 0, -1. This is 1 and -1. And of course, I didn't specify what this function is defined on the breakpoints, the boundary, -1 and 1 or 0, because we don't really have much control over that. Remember, when we compute the Fourier series, those points are forced. They end up being the average value between the top and bottom breakpoints. Okay, so let's first compute the solution to the homogeneous equation. So that's yh double prime plus 3yh prime plus 2yh equals 0. I'm not going to actually do this because we've done it before so much, this exact equation. You should remember that yh of x is c1 e to the negative x plus c2 e to the negative 2x. Or even if you don't remember that, you should know how to get that right away. Okay, so let's now look for a particular solution. So we are going to assume that there is a particular solution of the following. That's a Fourier series. So that's a naught over 2 plus the infinite sum from 1 to infinity of an cosine of n pi x over L. L is 1, so I don't need to write it, plus bn sine of n pi x over L. And now let's take derivatives of this and then plug it back in. So y p prime of x, so the constant term goes away. And I'm going to start omitting my 1 to infinities because those don't change at all. So now we have n pi an sine of n pi x. We need a negative sign out in front. And then plus n pi bn cosine of n pi x. And then a second derivative of this is going to yield almost the same thing. Let's see, now we have a negative n squared pi squared an cosine of n pi x, and we need a negative n squared pi squared bn sine of n pi x again. So now we are going to take these three and we're going to plug back in. So we're basically going to take this last one, y double prime, plus 3 of y prime, so 3 times this, plus 2 times this, and set it equal to the Fourier series of this square wave. And you may remember that that is actually equal to, maybe you don't remember, but it should ring a bell when I write it up, that this, well, being an odd function, contains only sine waves, and it is 4 over n pi, oh no, it's 2 over n pi, isn't it? Yeah, it's 2 over n pi times 1 minus negative 1 to the n. And the 4 comes from the fact that when n is even, this is 0, but when n is odd, we get 1 minus negative 1, and then we get a 4 there. Okay, so we're going to plug this back into the left-hand side, set it equal to, I forgot my sine of n pi x. Okay, let's do it. So, yh double prime, I'm going to write down negative n squared pi squared an cosine of n pi x minus n squared pi squared bn sine of n pi x. Now, plus 3 times these. So, plus a sum of negative 3 n pi an sine of n pi x plus 3n pi bn cosine of n pi x. And now we need plus 2 of these. So I'm not going to be able to fit this in one line. So plus 2 times a naught over 2, so that's just a naught, plus the sum of 2an cosine of n pi x plus 2bn sine of n pi x. We have to set that equal to the right-hand side. So what's the right-hand side? Well, the constant term is 0 plus 0 times cosine of n pi x plus 2 over n pi, 1 minus negative 1 to the n. I hope I gave myself enough room here. Sine of n pi x. Okay, so our coefficients here are 0 for a naught, 0 for an, and this guy for, so this is the bn's. So we need to collect these terms together. So the left-hand side, well, okay, what's the constant term? So the constant term is a naught. That is going to be equal to 0 because we're setting that equal to 0. And then plus, let's see, so what do we get? So we're going to get a cosine term, first of all. And what's that cosine term? So let's see, I'm going to use colors. I'm going to use blue for cosine and red for sine. So there's a cosine. There's another cosine coefficient, and there's another one. So there's going to be an an for all of these. So I'm going to write this as, let's see, so let's just do it. Negative n squared pi squared plus 3n, oops, let me undo that a little bit because I'm going to want an an there. An plus 3n pi times bn plus 2an, and this is all times cosine of n pi x. And then we're going to have a sine term, and what's the sine term? So that's going to be, so there's a sine coefficient, there's another one, and there's the last one. Actually, let me just go there. Okay, plus, so that's going to be a negative n squared pi squared bn minus 3n pi an plus 2bn, all times a sine of n pi x. So we have to set this thing on the right equal to this. So this is the left-hand side, simplified. This is the right-hand side. So now let me tweak this a little bit. Let me make this blue, and let me make this blue. So clearly, a naught has to be 0. And this blue term, has to be 0. So this has to be 0. And this term here has to be equal to that, to 2 over n pi times 1 minus negative 1 to the n. I said this was easier than Laplace transforms. Maybe you're not convinced of that. But at this point, we just have it down to algebra. So now we have a system of two equations. Let me write these down. So the first one, this thing equals 0. I'm going to group the an's and the bn's together. So the first one we have, how many an's do we have? We have 2 minus n squared pi squared, an plus 3n pi bn equals 0. And this second equation here, how many an's do we have this time? Now we have negative 3n pi an, and how many bn's do we have? We have plus 2 minus n squared pi squared bn. And now we have to set this equal to 2 over n pi, 1 minus negative 1 to the n. Okay. So now let's solve for, I don't know, one of these. Let's solve for, what do you want to solve for, an or bn? Let me just solve for bn. Why not? Because I like having simpler denominators. So here, bn is equal, so I'm going to move bn to that side, and I'm going to divide through by 3n and by negative 1. So I'm going to get n squared pi squared minus 2 over 3n pi and an. So this is what bn equals in terms of an. Now let's plug this back into here. So now we are going to get, I don't know if I'm going to have room for this, negative 3n pi. I'm going to factor out the an, so I'm going to just write, let's see, so what do we have? Now we have this thing times that thing, that's squared, so I'm going to say that's minus n squared pi squared minus 2 squared. So these are the same things, just up to a sign, and now I have to divide through by 3n pi. And once again, that times that is squared, and there's a negative sign that pulls out because I've put the order of this. So this whole thing times bn equals 2 over n pi 1 minus negative 1 to the n. So now I have an explicit formula for bn. I don't know if it's worth writing it down. First of all, I can combine these fractions. So let's divide. So let's first of all make this plus plus and then put a negative sign over there. Let's divide by n pi and square that up top so we can add these things together. So now if I do this, I get that, I'm going to do this in black now, bn, so what am I doing? I'm taking this thing and dividing it by this. Well, first of all, we can also cancel the n pi's here and there. So let's do that as well. Let's cancel n pi, n pi, n pi. And now bn is negative 2 times 1 minus negative 1 to the n. And I have to divide through by this thing. This might simplify. Let's see, does it simplify? I think it probably does, but I'm just going to leave it. So the bottom is going to be n squared pi squared minus 2 squared plus 3n squared pi squared. Okay, so that's my bn. It's an explicit formula for that. I've already said that my a naught is equal to 0. And now what's an? Well, an is right here. I can write, let's do that up here. Let's say that an is, let's see, what is it? It's negative 3n pi over, actually I'm going to make that positive 3n pi because I'm going to make this a n squared pi squared minus 2 times bn. And so we can just take this bn and multiply the top by 3n pi and the bottom by this. Things will probably cancel a little bit, but we don't really need to. So I'm just going to leave this as negative 2, 1 minus negative 1 to the n times 3n pi over n squared pi squared minus 2 times this n squared pi squared minus 2 squared plus 3n squared pi squared. Okay, so there's probably about a 50-50 chance that somewhere in here I made some stupid, careless little mistake. So like I dropped a sign or divided instead of multiplied, something like that. Very possible, but hopefully you can, if you see that, just ignore it. Basically what we did here is we found a particular solution. We found that there is a particular solution to this ODE that is a Fourier series. And in that Fourier series, the constant term is 0. AN is this expression, and BN is that expression. Not too helpful unless you have a computer and you can plug these things in directly and you can actually plot what that looks like. So I'm not going to do that, but if you are interested in MATLAB or Maple and you use these, I encourage you to try it yourself. So, as I said before, this maybe I didn't convince you this is easier than Laplace transforms, but it's not any harder. At least Laplace transforms, you have to use infinite. I think if you go back and solve something like this with a Laplace transform, you will find out that this is actually slightly easier, except for the algebra. But in the next example, I will do one where the algebra actually works out much nicer. And fortunately, that is a much more realistic one when it comes to physical models. So here's example 2. It's the same thing as before, except now we don't have this damping term. So it's y double prime plus omega squared y equals the same square wave. So once again, this square wave is n equals 1 to infinity of 2 over n pi times 1 minus negative 1 to the n sine of n pi x. Okay, so why is this easier? Well, it's because we don't actually have this y prime term, and we'll see why that simplifies things in a moment. First of all, let's solve the homogeneous part. So yh double prime plus omega squared yh equals 0. Hopefully you can do this by inspection now. So this should jump out at you as sines and cosines. So this is c1 cosine of omega x plus c2 sine of omega x. Okay, now let's guess a particular solution, yp of x. So is a Fourier series. Once again, this square wave is odd. I guess that's not too relevant here, but well, yeah, it is. So I'm going to assume that the particular solution is a naught over 2 plus n equals 1 to infinity of an cosine of n pi x over L over 1 plus bn sine of n pi x over L. Okay, now let's take derivatives and let's plug this back into the left-hand side. As before, right? Well, first of all, I only need to take one derivative, yp double prime of x. And I guess 2 derivatives, but I only need to write it down once. So if we do that, we get n equals 1 to infinity. We get n squared pi squared an times cosine of n pi x. And then we get, there's going to be a negative sign. Let me put that out in front. And then plus n squared pi squared bn sine of n pi x. Okay, so that's the second derivative. Now let's plug this back into the left-hand side and think about what happens. So when we do that, we're going to get a bunch of sines and cosines, right? But all of the ANs, actually, let me just do it and you'll see. So YH double prime is going to be negative n squared pi squared AN cosine of n pi x plus n squared pi squared bn sine of n pi x plus omega times this. So plus omega a naught over 2 plus n equals 1 to infinity. Here I guess I will put the indices on. Omega an cosine of n pi x plus omega bn sine of n pi x. and I want to set this equal to this thing here, which is 0 plus n equals 1 to infinity of 0 cosine of n pi x plus 2 over n pi, I need my omega here, omega, times 1 minus negative 1 to the n sine of n pi x. So once again, I'm going to set like terms equal. So my cosine terms are, there's one, and there's another one. I'm going to use a different color because I have it. I'm going to use orange for this. So there's my one cosine term. There's another cosine term, and that's equal to 0. And then my sine terms, there's one, and there's one. And my constant terms, those have to be equal. So right away, we get that a naught equals 0, and I claim we also get that an equals 0. Think about why that is. So let's set the cosine terms equal. So here we have negative n squared pi squared an plus omega an equals 0. Or in other words, negative n squared pi squared plus omega times an equals 0. And so, well, I guess it's possible that omega, well, this can't be equal for all n. So that tells us that an has to be 0. So that tells us that an has to be 0. Now let's do the same thing for the sine terms. So for the sine terms, we have negative n squared pi squared bn. So that's negative n squared pi squared bn, negative, plus, I guess I should have used some different color for the an's, but oh well, plus omega bn equals 2 omega over n pi times 1 minus negative 1 to the n. So I'm setting the coefficients of the sines equal to. And right away, I get what bn is. Bn equals, well, let's simplify this. So that's, what is that? That's omega minus n squared pi squared times bn. So bn is just this guy divided by omega minus n squared pi squared. So bn is 2 omega 1 minus negative 1 to the n over n pi times omega minus n squared pi squared. And that is it. So our final answer is that y of x equals, or yp of x is n equals 1 to infinity of 2 omega 1 minus negative 1 to the n over n pi omega minus n squared pi squared times sine of n pi x. So this is a particular solution, and this is the homogeneous solution. So our general solution is y of x equals yh of x plus yp of x. Now think about what we could have done with some foresight. We could have said that instead of our particular solution having sines and cosines, we could have just said, some foresight, we could have said, let yp of x be just sine terms, n equals 1 to infinity of bn sine of n pi x, and we could have plugged that in to the left-hand side. Think about why that's going to work now that we're done with this. So if you do that, and you plug it in the left-hand side, what do you get? Well, you get, in this term, you get only sine waves, and in the y double prime term, because you take two derivatives, you get only sine waves. So the left-hand side would have contained only sine waves, we have to set that equal to the right-hand side, which had only sine waves as well. So we don't have this mixture of sines and cosines. So with some foresight, we could have avoided some of this needless cosine terms and just right away guessed this was the particular solution, plugged it back in, and it made things simpler. Now this should remind you of when you do undetermined coefficients. Let's suppose you have y double prime plus omega squared y equals sine of x. Normally you have to guess yp of x equals a cosine of x plus b sine of x, right? Because when you plug that back in, having a y prime term in here means that if you were to just have the sine term, you would get a cosine and you'd be in trouble. But this was a special case. You may recall that if you didn't have that y prime term in here, you didn't need that cosine term, and you could have right away just guessed it was b sine of x and plugged that back in, and you could have found a b. Okay, so that is a good place to stop. I know this was a long, messy lecture, but hopefully you can see how we are now able to solve ODEs where the forcing term are these piecewise functions. And actually, this is something that you could program a computer pretty easily. There's nothing really messy here other than algebra. Okay, so that is a good place to stop. Next time we will study Fourier sine and cosine series. Those are a little bit different than regular Fourier series. And this is something that was actually invented to solve partial differential equations a couple hundred years ago. So stay with us.